Hey there, just a quick but really important video on the idea of time constant. This is an idea. The time constant is something that shows up in mathematical functions where you have like a negative exponential. We've seen it with terminal velocity uh, problems with that situation. We also see time constant with RC circuits, resistor capacitive circuits. So just a couple words on this and why it's useful. First of all, I've got plotted the two functions that keep popping up in a lot of these situations, okay? So the first function here is the negative exponential, e to the negative t over tau, okay? And the second function is 1 minus e to the negative t over tau. Now, what you might not recognize there is tau, right? And tau is actually what we call the time constant. For example, when you're dealing with RC circuits, tau is actually equal to something specific. It's equal to the resistance of the circuit times the value of the capacitance, right, as an example. So what is that? Why do you have this time constant? Okay, so first of all, one thing you should know about this is that what are the dimensions of tau? Like what is it seconds? Is it force? Is it energy or what? And the answer to that is if you look just carefully at the fact that you're dividing time, like lowercase t in seconds on the top, by tau, you should be getting something which is unitless, right? Whenever you have an exponent in equation in physics, there can't be any units with that. And so that basically tells you that the units for tau have to be seconds. And that way, you don't end up with any units when you divide seconds by seconds. The same thing happens over here, right? You can see the argument to the exponent, again, is that. So this is why it's called a time constant. So somehow, whatever tau is, it does have the units of seconds. And the question is as well, what's the meaning of it? So to show you that, I'm going to make a table underneath our graphs here. And we'll see the time constant is just a really useful thing in general. Add this out here. Okay, and so what I'm going to do is I'm going to make time the variable t, lowercase t, my first column, and then I'm going to evaluate the functions that are graphed up above. And you might be wondering, well, how can I do that, unless I have, if I don't have any numbers? And here's how. So for my time, I'm going to basically express time in terms of tau. So the first time I could have would be 0, right? So I could say that's 0 times tau, which of course is 0. Now, if I wait a little bit longer, I would have 1 times tau, right? So you have to think about tau as just like a number of seconds, right? Make up a number. Maybe tau, for example, is equal to 5 seconds. So this first point is 0 seconds, then 5, and let's keep going. So 2 times tau, 3 times tau. We're going to go all the way up to 5. Okay? And we're not actually using any specific value for tau. We're just going to do this without that, and I'll show you how that works. Okay, so let's go with this first function now. Let's evaluate this. So I'm going to plug in e to the negative, and then for t, well, that's 0 divided by tau. Well, e to the 0, right, is just going to be e to the 0th. And anything raised to the 0 power is simply equal to 1. Okay, so that's not bad. Now let's do the next one. Let's go to this one. So this is e to the negative tau over tau. See how I'm just substituting this in for t? And that's e to the negative 1. Okay, and you can calculate that on your calculator, go ahead and try it out. I'm going to do it on my phone. And so I get 0.37. Okay. And what that means is that my function is now gone from basically 1 down to 0.37. So I've dropped down to 37% of what I started with. So let me go up to the graph, right? So if this is 1 up here, then by the time I get to 1 tau, I'm now down to 0.37. It's supposed to be a line there, okay? So if you have a time constant, it's characteristic of the exponential decay. And it means that no matter what exponential decay you have, that if you wait for one time constant, you'll be down to 37% of whatever you started with. Okay. Now you can go ahead and do the rest of these. You can imagine the next one would be e to the negative 2, right? And then e to the negative 3, all the way down to e to the negative 5. And go ahead on your calculator and calculate those decimals, or if you like, those percentages. Okay. You can pause the video as you do that. But one of the things you'll notice now that you've tried it is when you get down to this last case here, for the very first time, you're now down to something which is less than 1%. So it's 0.00, it's about 0.007, right? I'll circle that. That's about 0.7%, right? Moving the decimal over. So if you wait for 5 time constants, if you let an exponential decay happen for 5 of these characteristic time periods, you will be down to less than 1% of your starting value. Okay? This is true for any exponential decay. So this is sometimes called the 5 tau rule, right? And that means that you're less than 1% with this first function, right? It drops down to that much, and that applies to anything, right? All right. Now, if you go to the other side here, if you look at the other flip side, sometimes you have exponentials which go up like this, and they approach an asymptote, right? Right. And so the asymptote in this particular problem, or this particular example, is just 1, right? Because here it is. So go ahead and try. You don't have to use your exponential button anymore, but try to do 1 minus, well, 1, right? And so your starting point here is, of course, you're starting at 0. So the value of this function starts at 0. This might be like the charge on a capacitor when you first begin to charge it. Now, when you go to 1 tau, again, you're going to do 1, right? This is the one I'm still talking about, the one from up above. But then you subtract 0.37. Now that turns out to be 0.63. And I guess I'll circle these, right? And so this means that if you wait around for 1 tau here, that you're up to 0.63. You're up to 63% of your maximum. You're 63% of the way to the asymptote of that graph. Okay, so that's a lot, right? For one time constant, you're already 63% the way there. So I'll let you continue, and you can do the next several cases. But when you get down to this 5 tau case, you're going to see that for the first time ever, that now you are actually something around 0.993 or something like that. And that's 99%. And so if you wait around for 5 tau, which are going to be someplace like way out here, 5 tau, that's when you're 99% of the way there. Okay. And so that's true for any exponential function. So things I like to remember, I like this 5 tau rule because with an exponential function, you're never truly there. You're always approaching some asymptote. But if you want to say, when am I 99% of the way there, right? then I can say, well, just find what are 5 times the time constants, and that'll help me with that. The other set of numbers I like to remember is I kind of like to remember this number, the 37% and the 63. And those are the ones that I showed on the graphs here, right? And those are easy to generate because each of those is just, it's e to the -1 is 37%. And then if you subtract that from 100%, you get 63%. So it's probably just good to know that. Exponential functions pop up all over the place in physics and in science. And you should know that the one-time constant will take you to those two places. Okay. So hopefully that helps you out. By the way, if you're solving problems with capacitors, for example, you can probably show yourself that if you simply multiply ohms times farads, right, like here, you actually end up getting seconds. And that's an interesting exercise if you can figure out how that works. But anyway, multiplying ohms times farads will give you seconds. And then you can use that information to, solve problems and make predictions about, time constant things. Okay. All right. Have fun.